Afternoon, Bangkok. My name's Tim Cooper, and I'm here to talk to you today about the best practices to use when you're creating UIs using the UI system we introduced in Unity 4.6. Now, since the UI system's been released, we've seen a lot of great things being developed. One of the bad things, though, is that people haven't been necessarily constructing their content in a way that leads to the best performance for their systems. So what we're going to do today is go through a walkthrough and a step-by-step guide on how to optimize your content for the best performance in the system. So there are a few takeaways from this talk that I will hope you will have. The first is I hope you understand some of the best practices in order to author high-performance systems and user interfaces. Understand how to use the Unity frame debugger and how to optimize your scenes based on this. Understand the concept of batching, why it's important to your scenes, and how to maximize it, as well as write optimized custom UI components. So who am I? My name's Tim Cooper, and I've been a developer at Unity Technologies for the past 4 years. Before this, I used to be a graphics or core programmer and worked on computer games, but I've been working on the UI for the past 2 years. Let's start this presentation by going into some terminology associated with batching. So, what is batching? When you have a scene in Unity or any other game engine, every frame it will render a number of meshes. Now these meshes are rendered in a specific order to the screen so you can see what exists in your game world. Every time you have a render call, it requires a specific state to be drawn. And this state depends on a number of things, such as the material your mesh has, the texture your mesh has, and a number of other properties. It's like when you render a mesh, it requires a specific brush to be drawn, to use a painting analogy. If Unity needs to change to a different state to draw a mesh, this requires an internal state change in Unity. And this can be a little bit slow. As an optimization, internally, if you have multiple meshes rendered in a row that use the same state, Unity can combine these into a single mesh. What happens is this mesh now renders in one draw call, and we call this a batch. This works because these meshes share the same state, the same material, and the same texture, and no state change is required. For normal scenes, this can be achieved by using either static or dynamic batching. For static batching, this happens when your scene is built, but for dynamic batching, this happens dynamically at runtime, depending on what's visible on the screen. And for the UI, it's a little bit different, which is what we'll cover in a moment. The process of combining these meshes into one mesh and one draw call is called batching. If you look at the top here, you'll see that we have combined 6 meshes into 3 draw calls. If you have a different material or a different texture than a previous batch, a new draw call is required. And we talk about breaking the batch in this situation. And this is a term we give when a state change is required internally. If you look at the top graphic, you'll see that we have 5 meshes being drawn, and they all have the same material and the same texture. On the second row, though, we have 6 objects being drawn. And in the middle, the object is using a different texture, so the batch becomes broken. When it comes to state changes, some are faster than others. For example, a simple material property change, like a texture, is considered relatively fast, whereas changing the material itself is slow. A slow state change will happen whenever a material is changed. This is because internally, Unity must change the shader that's being used, and this is a slow process. What happens internally is that Unity needs to rebuild the render pipeline and update things like blending states. If you open the statistics window in the game view, you'll see there are two things that are interesting here. There's a field for batches, and there's a field for set pass. Whenever a slow state change happens, the counter to set pass will be incremented. And whenever a draw call is issued, the counter to batches will be incremented. Whenever a set pass call happens, you will always be rendering a batch, so the set pass calls will always be at least as high as the batches count. And the batches will always be equal to or greater than the number of set pass calls. Now, a fast state change occurs whenever a texture is changed. When this happens, the material can stay the same because they're shared between the two draw calls. And the internal rendering state, for the most part, stays the same. The only thing that needs to be modified are some of the shader properties or uniforms. Because we're not changing the material, all we have to do is update these uniforms to the currently bound shader program and then issue another draw call. This is relatively fast compared to changing the material. If we take a look at this graphic, you'll see that in the top row, we have 6 elements being rendered, and in the bottom row, we also have 6 elements being rendered. The top row has 3 batches, but because the material is shared, there's only 1 set pass call. Whereas in the bottom call, we have 3 batches and 3 set pass calls. This is because the middle element is rendering using a different material. So let's talk a little bit more about batching and what it means for the UI system. What we're going to do is we're going to start by having a look at a UI scene that has batching enabled, and then another UI scene that has batching disabled. Sorry, the other way around. So as you can see, we have a scene from the UI example project. It consists of many logical elements, but if we look, it renders in 14 draw calls. This is relatively inefficient because you'd expect these elements to be combined and render in a single draw call. If we now enable batching, and as you can see, this is the same scene with the same logical elements, it will now render in just 2 draw calls. If we take a look here in the frame debugger, you'll see that 1 draw call is for the background and 1 draw call is for the foreground text. This is much more optimal than the previous example. So how does batching get calculated? As you saw earlier, it's based on a number of rules, such as material changes or shared material properties. In addition to this in the UI system, we also look at which elements overlap, because if elements overlap, they can potentially not be batched together if they have different materials. What this means is that you need to configure your projects to take advantage of batching in the UI system. And for that to happen, you need to understand how your content is created, the textures you're using, and the materials you're using in your scenes. Now, before we start looking at the rules associated with batching in the UI, let's take a look at the Unity 5 frame debugger. Now, this is a new tool we introduced in Unity 5, and what it allows you to do is step through the individual draw calls that are issued to the rendering pipeline in Unity. It's the easiest way to see what gets rendered in one draw call, and it's a tool that exists within the editor. As a note, this tool isn't just for the UI system, it's for Unity in general. So anything that you render in Unity, you can look at through the frame debugger. So how do you use it? Let's have a look. So here we have a simple scene that uses the UI system. And if we go to the window menu, you'll see there's a drop-down for the frame debugger. If you click this, you'll get the frame debugger window appearing. When you enable this tool, you'll see that it becomes populated with the draw calls that exist in the scene. By sliding this top bar, you can drag through the individual draw calls as they're issued to the video card. The left panel has information regarding the current rendering events, and normally the entry point is for camera rendering, then followed by opaque scene rendering and transparent rendering. If you select an element, you can step up and down, and on the right-hand panel, it'll give you information about that specific event, such as the shader that's being used, the current material properties, and information about the vertices and indices that are being rendered. If you have a normal scene that has lighting and shadowing, this will also display the shadow rendering and other things. So you can use this extensively for scene debugging. So let's go back to batching. When it comes to the UI system, batching happens on a per canvas basis, and this includes nested canvases. What this means is that you can use nested canvases to specify different subsets for batching regions, and it also means that if you have similar elements on multiple canvases, they won't batch together as they don't share mesh data. So what are the rules? So the first rule for batching in the UI system is that for elements to batch together, they must share the same material and the same texture. Here we have two elements, and as you can see, they render together. In the scene view, they are logically separated, so they're easy to use, as you'd expect. If you modify the the color on one of these elements, you'll also see that it still batches together. This is because we're not modifying the texture or material data, and instead, the color is specified to the color stream of the vertex buffer. To extend from this rule, overlapping elements that use the same material and texture can still batch together. This is because when we specify the vertices to the graphics card, we specify them in the correct order to render in a back-to-front manner. The second rule that we will move on to is that batches will be broken when a material or texture change is required. Now, the simple case for this is if you have multiple elements in your scene that actually have separate materials or separate textures. Because of this, the elements cannot batch because they require separate rendering state, and because of this, separate draw calls are required. In this example, we have two elements which have different textures. If we step through the frame debugger, you'll see that they render in individual draw calls. This is because they cannot batch together. Let's move on to a less simple case, and this is if you have overlapping elements. Elements that are overlapping need to be rendered in the correct order. Now, if these elements cannot batch together, that means we need to break the draw calls, or to break the batch in between them. Let's have a look at an example so it's a little bit clearer. In this scene, we have 3 squares, and in the middle square, we are using a separate material. Because a separate material is used, these squares can't batch together. And even though the 2 outside squares share the same material and texture, we need to break the batch so that the overlapping is correct. This brings us to the next point, which is batch sorting. Sorting is a concept internal to the UI system, and what it does is it uses rectangular overlaps to calculate what can batch together. For a given set of input commands or input render commands, Unity will attempt to rearrange the draw order to achieve the least material changes and the least texture changes, essentially breaking the batch as little as possible. The biggest restriction of this is that the output needs to appear the same as the input. So take, for example, this scene. Let's say an input order was specified as is in the top row. Now, as you might have seen yesterday, this ordering is specified in the hierarchy window as a back-to-front ordering. What Unity will attempt to do is rearrange this order into an optimal state. The bottom row is a perfect example of what could happen, but given how content is created, it is unlikely. It'll probably be somewhere semi-optimal, but not as optimal as the bottom row. In Unity 5.2, we're introducing a special rule, and that is that only elements that are co-planar with the canvas will sort correctly for batching. Before Unity 5.2, we only considered element overlaps in the 2D plane, and this could lead to some severe issues if you're using a perspective canvas or have elements offset from the canvas. Let's see what it looks like in the current version of Unity, and then we'll have a look at how we solve the issue. So here we have 3 elements, with the red circle rendering in between the 2 green squares. In the 2D view, this looks correct. But let's change to perspective. If you have a look here, you'll see that the red square, whilst specified to render in between the 2 squares, in fact renders in front of them. This is because the batch calculation was happening in the 2D space, and it thought that the elements were not overlapping. So in Unity 5.2, we have a new rule for this, and that is when this situation is encountered, we break the sorting, and this fixes the issue. Depending on your content, this may or may not cost more draw calls. This doesn't necessarily break a batch, is what this means. Let's take a look here at what happens when we have the fixed code. As you can see, the scene is the same as before. Yet now the red circle renders correctly in between the squares. If we enable the frame debugger, you'll see that we have unfortunately needed to break the batch to do this. So in Unity 5.2, we have slightly affected performance at the cost of correctness, and we believe this is the desirable outcome in these situations. So what will make an element break coplanarness with the canvas? There are a few things that can do this. If elements have a different Z value from the canvas, it will break coplanarness. If the elements are rotated outside of canvas alignment, it will break coplanarness with the canvas. Or if you specify a 3-dimensional input mesh where all of the vertices are not aligned with the canvas. So here we have that same scene as before. If you have a look in the frame debugger, you'll see that currently this renders in 4 draw calls. This is because the elements are coplanar with the canvas and batching can be correctly calculated in the 2D plane. If we rotate this circle outside of that boundary, you'll see that the draw call increases to 5. Let's undo that. Now if we move this element backwards off the canvas, you'll also see that we once again increase the draw call to 5. Finally though, if we rotate this element within the plane of the canvas, the draw call remains at 4. This is because coplanarness does not get broken in this situation. So to summarize those rules that we talked about, if Unity needs to modify the material when rendering, we'll break the batch. If a texture change is required, we'll break a batch. If elements are offset from the canvas, we'll break sorting, which may or may not break a batch, depending on how your content is constructed. So let's talk about how you can apply these rules to your scene. The first thing to do is attempt to minimize material changes in your UI. It's important to have different materials, but you should use them sparingly, such for things like effects or other special events. In all of the UIs we construct internally, we try and use a single material for most of the UI and only use other materials for special things. Prior to Unity 5.2, text and normal UI elements could not use the same material, and this caused a slow state change. From Unity 5.2 onwards, this isn't a problem. The next thing to note is you should attempt to minimize texture changes in your UI. This isn't to say don't use a lot of textures, because we feel that would be artistically limiting. What this means is use features like the sprite atlasing and other tools in Unity to reduce the textures into a single atlas. We'll cover this in a moment. As an extra note, text is currently not put into a sprite atlas, and this can lead to increased draw calls. As a final note, as of Unity 5.2, try and keep your elements co-planar with the canvas. To do this, you can use features such as nested canvases if you wish to have rich 3D scenes. It's okay to move some elements off the canvas, but be aware that this will break sorting. We use this extensively for things like buttons that pop out of the screen and similar, but try and make this the exception rather than the rule. So let's take a UI scene and optimize it using these steps we know now. So here's that scene we were looking at earlier. And as you can see, it currently has 25 draw calls. This is quite excessive, as you would expect things like the background elements to batch correctly together, and also the text to batch together. Let's have a look at the scene and try and figure out why it's currently working the way it is. If we select the canvas, you'll see that, to start with, all of the elements in the scene are offset from it. As discussed earlier, this breaks one of the rules we talked about. The elements in the scene are not co-planar with the canvas. So the first thing we're going to do is we're going to have a look at these windows, and we're going to add a canvas element to them. By using the nested canvas feature of the UI system, it's possible to make all of the elements here co-planar with the canvas. Now if we have a look in the frame debugger, you'll see that we've already reduced the draw calls by 12. If you have a look at the window here, you will see that the settings title is currently offset from the canvas, and this will break sorting, and this has led to a few extra draw calls. Let's not address that for now. The next thing to look at is why some of the background elements are still not batching together. Let's take a look at the window that lives in the background. Currently, the sprite that's using is the SF window sprite. If we look at the foreground elements, though, they're using the title sprite. This breaks one of the other rules we talked about earlier. These elements are now using separate textures, which means they cannot batch together. What we're going to do is we're going to use the sprite atlasing feature that was introduced with Unity 2D to put these textures into the same atlas. To do this, what we do is we select the textures and add a packing tag. We then open the sprite packer window and press the pack button. What this will do is it will pack those textures into one atlas. This means that when we render, they can use the same texture even though they're using separate elements. This means that they can render in one draw call together. Let's quickly enter play mode and have a look at what that looks like. So we've reduced the draw calls some more now. Firstly, we're rendering the whole background together. Then we're rendering the offset text because sorting was broken. Then we render the buttons on the background and the text at the front. So this is 1, 2, 3, 4, 5 draw calls for this element. This is much more optimal, but it's still not perfect. If you want to take this optimization to the final step, what you can do is also make these elements co-planar with the canvas. And now when we enter play mode, you'll see that we can have this canvas element render in 2 draw calls. We haven't applied all of the same optimizations to the left panel yet, so it is not as optimized. So by using these steps, we reduced the rendering of one panel from something like 15 or 13 draw calls down to 2, and we can do the same for the left-hand panel. So essentially, we can have this UI render in 4 draw calls. This is a significant optimization. So we've talked about how we perform batching in the UI system to reduce draw calls and state changes. But batching has to be regenerated at certain situations, depending on when things change. So let's talk about the canvas render element. Every UI element you have in your scene has a canvas renderer associated with it. Now, what the UI elements we have in the UI system do is they configure this canvas renderer with data, such as the texture, the mesh, and the color. So what happens when you modify one of these canvas renderers? This causes a situation we call rebatching. And this means internally, we need to recalculate all of the batch data. Now, there's a few reasons for this. If you modify a material or texture, you may modify what things can batch together, so we need to recalculate that. If you modify a mesh, you can modify what overlaps with another element, and this can also affect the output status. Now, this process is not slow, but it's also not fast. So we recommend performing it as little as possible, although in some systems, this is not possible. Another thing that can cause rebatching is rearranging the order of elements as specified in the hierarchy, or changing the sibling order. When this happens, Unity needs to recalculate the draw order of the elements you're rendering. And to do this internally, we need to iterate all of the canvas renderers on a canvas and then perform a rebatch operation. This is much slower than a standard rebatch, and we recommend avoiding this wherever possible. Luckily, this is something that happens infrequently. A situation where this can occur is if you, say, have a windowing system, and if you click one of the windows, it brings them to the front. We need to reperform this because you've changed depth values. A further note is that on the canvas, we support a property called pixel perfect. What this does is it snaps the rect transform generated pixels to pixel boundaries. And this happens whenever a rect is moved because you may have changed pixel boundaries. And this includes children. This means that if you're using pixel perfect, we need to regenerate vertices whenever anything is moved. And this is quite slow. As a note, pixel perfect only works on screen space canvases, such as perspective or overlay canvases. What does that look like and mean, though? So here we have a scene where we have an element, and if we move it, you'll see that it moves freely, and the pixels are correctly bound to the edge of the rect transform. If we enable pixel perfect on the canvas, though, you'll see that the pixel boundaries do not match the rect transform exactly. They snap to the pixel grid in the background. Doing this calculation can be a slow process. So as you saw, snapping the vertices means regeneration, and this is slow. So for speed, we recommend disabling pixel perfect on canvases where elements move. Another possibility you can use is you can disable pixel perfect at the start of the movement, but then re-enable it afterwards. Normally what we do in our scenes is if we have heavily dynamic elements, we place them on either a nested or separate canvas and just disable pixel perfect on that canvas. Let's start looking at optimizing custom UI components. This part of the talk will delve a little bit into programming and is mostly applicable to people who are writing custom components using the UI framework. So we have a different number of type of controls we support in the UI system, such as graphical elements and layout elements. Now, you can write your own of these, and this can modify what is rendered or how a layout exists. A graphic component is commonly used to modify the canvas renderer and the things that are being drawn on the screen, whereas layout components normally control the rect transform. You could write a custom component that combined these two things, but we think they are quite separate, and we try and keep them that way internally.